Welcome to this session, the first session, the mathematical machinery of quantum mechanics. So this is a very important session because this is the last chance you have in order to be able to understand what the stuff that we will go through from a mathematical point of view with Carlos. So it's a pleasure to have Maria, one of the mathematicians who recently joined our company to work with us in our transition to industry. So I'll hand over to Maria, who will take you into this fascinating world of Hilbert spaces. So maybe Maria, you take over and introduce yourself, and off I go. I'm off.
Thank you, Bamurde. So hello everybody. The most difficult thing that we are going to learn today is my name. Is Maria Eugenia Celore Ramirez, 2 words for my name, 2 words for my surname. If you got that, everything else is going to be super easy. So I have been working in Banach algebras for my PhD. So my background is really, really pure mathematics. So this is what I'm going to do today. I'm going to introduce the pure mathematics tools that we need for the quantum mechanics. If you have questions that refer to the physics, I am afraid I'm not going to be able to help with that. But if you have questions about mathematics, that's going to be where I can give you a hand. So if anybody cannot see that I'm sharing my screen, now is the time to say it. So I'm going to start with an introduction to Hilbert spaces today. And I am going to apologize because today is going to be a little bit, I don't want to say boring, but less interactive and less entertaining, because we're going to go through a lot of definitions and the cool mathematics are going to start in the next session. So the first thing we are going to see is we're going to talk about vector spaces, linear subspaces, and inner product spaces. And this is already going to start sounding like something that you might be interested in. Then we're going to jump and we're going to talk about what are norms and what are norm spaces. And we are going to see that actually inner product spaces are norm spaces. They are actually a very specific kind of norm spaces. And we're going to talk about a couple of theorems, and the most important one is going to be the parallelogram law. And later on, we are going to talk about sequences, convergent sequences, Cauchy sequences, and we're going to see what is to be complete. That is going to lead us into talking about Banach spaces and Hilbert spaces. And we're going to see a characterization of Hilbert spaces as part of the Banach space structure. And then we're going to end up the session seeing a couple of examples of Hilbert spaces. Hopefully, everything will be clear, but if not, please ask, write in the chat if there is something that needs clarification. Okay. So we are going to start with vector spaces. So given a field and a set, and I'm going to make a remark here. If you already know what is a field, then that's great. If you don't know what is a field, this is completely new for you. Just think about R and C. Actually, we're going to focus on those, but I just wanted to make a slightly more abstract definition for the people that know about this. So given a field, the real numbers or the complex numbers, and a set, we are going to consider 2 operations. One is going to be an addition that takes 2 elements from the set and add them, and we end up in the same set. And we're going to have a scalar multiplication that takes a scalar, so an element of the field, and an element of our set V, and it multiplies them. And we end up again in V. Now, these 2 operations are not any operation. They're going to satisfy some things. The first one is that the addition is commutative. We also have that the addition is going to be associative. We are going to have a 0 vector. I'm going to start writing it like this to clarify that is the 0 vector, but at some point, and in the literature, you're not going to find it with a subscript. It's going to be just written as 0. So it's just a matter of keeping track if we are talking about a number or a vector. So this zero vector, what happens is that whenever we add it to any other vector, it's like if we were doing nothing. So we just keep the same vector. Then we have, for every vector in our set, we have an inverse vector with respect to the addition, which we're always going to write like minus b. And whenever we add them together, we obtain the zero vector. When we multiply by the unit of the field, again, it's like if we were not doing anything, we obtain the same vector. The scalar multiplication is the same to multiply by a scalar and then multiply by another, or to do the multiplication first and then multiply by the vector. Is distributive with respect of the addition in the set V. And also is the addition in the field is distributed with respect to the multiplication in the set B. So this is a whole lot of characteristics of things, and whenever we satisfy all of them, we have an F vector space or a vector space over the field F. So whenever we say a complex vector space, we are saying that we have a vector space over the field of the complex numbers, or a real vector space is a vector space over the field over the real numbers. So we will focus in the real or the complex numbers. I think specifically we are going to focus in the complex numbers, but the reals are going to also be useful to keep in mind. Cool. So let's see some examples. I think everybody is going to be acquainted with the set of Rn for any n. This is an R vector space. The square matrices with entries on R is also an R vector space with the usual addition and scalar multiplication. Maybe the most interesting one of these very basic examples is the set of functions that go from R to R, where the addition is defined in the following way. Whenever we add two functions f and g, and we apply them to an element, this is the same as applying f to the element and add it to g applied to the element. And the scalar multiplication, we define it in a similar fashion. Whenever we multiply a function by a scalar and apply it to an element, is the same as if we multiply the scalar by whatever we obtain applying the function to the element. Now, I'm not going to go into the proof that these are vector space, but if you have never seen this notion, it is a really nice exercise to start proving that actually these three things that I've said here are vector spaces. To do that, the only thing you would have to do is to take all these characteristics and verify that whenever we take vector in Rn and another vector in Rn, we can, the sum is associative, commutative, etc., etc., etc. So you will have to go one by one and check that all these are satisfied in these sets. Cool. So now that we have seen vector spaces, we will talk about linear subspaces of vector spaces. So we have a vector space. And now we have a smaller set, double V, that is a subset of this V. We want to know when we are going to inherit this vector space structure. That's going to be really useful because if we know how to do this, whenever we have something that is lying inside of Rn or anything that we already know that is a vector space, then we know that it would be really good to know when it is also a vector space. So we say that double V is a linear subspace of V, sorry, I missed the linear, if it satisfies the following. The zero vector that was before in our V is also in double V. For any scalar, whenever an element of double V, whenever we do the scalar multiplication, we are still in V, in double V, sorry. And whenever we have two vectors in double V and we add them, we are still here. So what is happening? What I'm checking with this is that if I continue doing operations, the two only operations that I know for now, which is addition within the set and scalar multiplication, I remain within the set. If I remain within the set and my zero vector is inside of the set, of this small set or the subset, then we're going to inherit the vector structure. So in another nice exercise, if you want to do it, is to prove that if we have these three things, if these three things are true, then all the other 8 or 9 characteristics that we said a vector space has are going to be true for double B. Cool. And now we're going to jump and talk about inner products. I'm sorry because there is another definition coming, another set of actions that this has to satisfy. So we have a vector space over the complex numbers. From now on, we are always going to be talking about vector spaces over the complex numbers. So if I miss over C, just assume is that. From now on, that's going to be your case. So we have a vector space over the complex numbers, and we have a mapping that goes from, takes two elements of the vector space, does something, and we end up in the complex numbers. We say this mapping is an inner product if it satisfies three things. For any two vectors, doing the inner product of x and y is the same as doing the inner product of y and x and taking the complex conjugate. Remember, we are finishing in C, so we can take the complex conjugate there. This mapping is linear in the first variable. So for now, only in the first variable. That's by definition. If we are multiplying by a scalar and adding with another thing, we can take the scalar out and separate the two inner products. And the third thing that an inner product must satisfy is that whenever we take the inner product of an element by itself, first of all, this is hidden in this statement. This inner product of an element by itself is a real number, which is always greater or equal than 0, and is only 0 if and only if this vector is the 0 vector. So if we have a mapping that satisfies these three things, we have an inner product. Now, we have only talked about what happens in linearity with the first variable, but from these things, we can deduce that it's actually every inner product is conjugate linear in the second variable. How do we see that? Well, let's see what happens when we have a scalar multiplied by a vector in the second variable. By the first characteristics that we just saw that inner product have, this is the same as if we change the order and we take the complex conjugate. Now, because we already saw that it was linear in the first variable, we can take the scalar out of the inner product. Remember, we are taking the complex conjugate over all of it. But we know that the complex conjugate of a multiplication is the same as the multiplication of the complex conjugates, so we can just take it out. And by using, again, the first property of an inner product, we can come back to the inner product of x and y. So if we realize the inner product of x and y and alpha y is the complex conjugate of alpha times the inner products of x and y. So this shows that the inner products are conjugate linear in the second variable, and this is a property that we have to be very careful because we tend to think, oh, is linear in the first variable, is linear in the second one. That's not the case. And this is just a small remark. Whenever we have a vector space with an inner product, we call it an inner product space. And in some literature, you're going to see it as a pre-Hilbert space, which I think already shows how important these inner product spaces are for Hilbert spaces. And we are going to talk now about norms. Another definition. I'm sorry about this. So what is a norm? Well, when we have a vector space, a norm is a map. The idea is that this map is going to give us the length-ish of the vectors. If you think about Rn, basically a norm is just an abstraction of that, of finding the length of these vectors, of vectors in Rn. How is this abstraction? So it's a mapping that satisfies, again, some conditions. The first condition, it seems very natural. The length is never going to be smaller than 0, so the norm of a vector has to be greater or equal than 0. And it's going to be 0 if and only if the vector is the vector 0. Whenever we multiply a scalar times a vector, and we take the norm, that's going to be the same as taking the modulus of the scalar times the norm of the vector. This seems very natural. And we have a sort of triangle inequality. If we have the norm of the addition of two vectors that is less than or equal than the addition of the norms of those two vectors. Whenever we have a vector space with a norm, that is what we call a norm space. There is something else that I'm not going to talk about, but are metric spaces. Metric spaces is like the thing that comes before norm spaces. Depending on the literature, that might be the starting point. I'm going to recommend some books later on, and they are going to talk a little bit about vector spaces, but it's not going to be important. I could have continued without mentioning them, but I do not like to do that because sometimes if you are going to look for this, they are going to appear, and it's going to lose some meaning. So basically, all norm spaces are metric spaces. Not all metric spaces are norm spaces. That's basically all I would like to say about this for now. Cool. But we were talking before about inner product spaces, and those seem like they were the interesting ones for Hilbert spaces. So what happens now with the norm? Well, actually, whenever we have an inner product space, we can define a norm, and that norm is going to be totally dependent on the inner product. The way of defining it is we just take the inner product of an element by itself. Remember, this was already a positive real number, so we can take the square root very easily. There is no problem with that. We're not going to do something weird. And we take the square root. That is going to be the norm of X, when X is an element of an inner product space. Then this thing that we have defined is a norm on E. Now, remember, a norm was a thing that satisfies these three conditions. So we have to check, if I can move on, we have to check that these three conditions are actually satisfied whenever I define the norm in this way. Cool. First one, we need to check that the norm of a vector is greater or equal than 0, and that is 0 if and only if the vector is the 0 vector. But this follows completely from the definition of inner product. Sorry, this is a typo. This shouldn't be here. We have seen that the inner product of a vector by itself is always greater or equal than 0, and is 0 if and only if the vector is the 0 vector. So this follows immediately. We have to check that whenever we multiply a vector times a scalar and take the norm, that is equal to the modulus of the scalar times the norm of the vector. This is, instead of considering the norm, I'm going to consider the square of the norm, just because square roots are a bit of a pain. If I can avoid dealing with them, that's better. And if we are squaring, it doesn't change anything, it's equivalent. So by definition of the norm, this is as taking the inner product of lambda x by lambda x. If we remember, it was linear in the first variable and conjugate linear in the second variable. So we can take this lambda out in as it is, and we can take this lambda out and conjugate, taking the complex conjugate. But a complex times in its complex conjugate is the modulus of that complex square. So we have arrived to basically this square, which is what we wanted. So it looks like we have 2 out of 3. And we just need to see what happens with this one. Now, in order to prove this one, that the norm of the sum of 2 vectors is less than or equal than the sum of the norm of the vectors, I am going to prove first a theorem, which is the Cauchy-Schwarz inequality. It's going to be really useful, and we're going to use it a lot. So I'm going to prove this one now, and then we will come back to that. So whenever we have an inner product space, E, this is the norm defined by the inner product. We have the following inequality. The inner product of x and y, the modulus of the inner product of x and y, is always less than or equal than the norm of x times the norm of y. This kind of seems intuitive. On top of that, we can say something else. We can say that we are going to reach the equality if and only if x and y are linearly dependent. So this is actually a really strong theorem because it's giving us a very nice bound for the modulus of the inner product, but it's also giving us an equality, and it's giving us the condition of when this equality is going to happen. So we're going to see the proof of this now. So whenever x and y are linearly independent, this means that there is an element in C, or a scalar, such that one of them can be written as a scalar times the other. So in this case, I'm going to just write that x can be written as alpha times y. So the norm of x is the modulus of alpha times the norm of y, and the norm of y is the norm of y. If we do this, so we have this equality really easily. Now, if we check what happens with the inner product, we have that the inner product of x and y, because of how x is, can be written in this way, is just the inner product. Sorry, I'm missing a modulus here, of alpha y times alpha y times y. Sorry. Remember that the inner product is linear in the first variable, so I can take alpha out, and I can take it out of the modulus as long as I remember to keep the modulus there. And so we have a modulus of alpha inner product of y by itself. But remember that this is just the norm of y squared, which is what we obtain here. So whenever f and y are linearly dependent, the result holds, the inequality holds, and actually we have the equality, which is what we wanted. So now let's see what happens when they are not linearly dependent. For that, I just wanted to remember that proving that the inner product of x and y is less than or equal than the norm of x times the norm of y is equivalent to proving that the square of this is less than or equal than the square of this, but that can be written in terms of the inner products. Cool. So let's consider x and y linearly independent. In particular, this means that y is not 0. The 0 vector is considered linearly dependent with everything else. So in particular, we have that y is not 0, and this is important because at some point we're going to divide by the norm of y, and we don't want to divide by 0. Whenever you're going to divide by something, please check before that is not a 0. So then, for any scalar, any complex number, we can take the inner product of x plus y plus alpha y by itself, which, because we already know that they are not linearly dependent, they are independent, we know that this vector is not the vector 0. So then by the properties of the inner product, this inner product is strictly greater than 0. And now we're going to just use the properties of the inner product to see what can we do with this whole thing. So if I can move. Go. Remember, the inner product was linear in the first variable, so we can separate things and take the alpha out. It was conjugate linear in the second variable, so if we do something with this alpha, it's going to come in the other way. Sorry, as the conjugate, complex conjugate. So basically, we are going to obtain this equality. The inner product of x by itself plus alpha times the inner product of yx plus the complex conjugate of the inner product of xy plus the modulus square of alpha inner product yy. Now, let's pay attention to these two. If we remember, by the properties of the inner product, this is actually the complex conjugate of the inner product of xy. So if we look at the whole thing, this is the complex conjugate of this one, or the other way around. We know that it's reflexive. So whenever we add a complex number plus its complex conjugate, we obtain twice the real part of the complex number. This is what is happening here. So we keep this one as it is, we keep this one as it is, and we just put these two together as the real part of alpha times the inner product of yx. Now, this is true for any alpha. So in particular, if I take this alpha, this is where I was going to divide by the modulus or the norm of y. This is why I needed it to not be 0. So if I take this alpha, it's still going to be true. So I'm going to take it and I'm going to substitute in what we got before, and let's see what happens. So we still have that whatever we do is strictly greater than 0. There was no alpha in this part. I already took the minus outside. The real part of a negative or something with a minus sign, you can take it out. I just put the alpha in here, and I wrote this as the complex conjugate. I'm going to come back for a second. We had the inner product of yx, so I'm just writing it as the inner product of xy complex conjugate. That's what happened here. And I just wrote my alpha inside of the modulus square and yy as it was. Now, if we keep in mind that this was already positive, so then this was also already positive, we can cancel one with each other. We can also forget about the absolute value because it's already positive. So we can write these two together. This one times this one is also going to be the modulus square of the inner product of x, y. We use that trick right above. So we have minus 2 of those plus 1 of these. That's where we are obtaining this one. And I just wrote this inner product of x by itself. I just wrote it with the same denominator. So I just need a yy multiplying there. So we have that this expression, is strictly greater than 0. Because we know that this is not negative, we can forget about it, and we get that the inner product of x by itself and the inner times the inner product of y by itself minus the modulus of the inner product of xy squared is strictly greater than 0. Now we can move things around, and this is equivalent to saying this, which is exactly what we wanted. So we have seen that whenever x and y are linearly dependent, we have the equality as we wanted. And whenever they are linearly independent, we have an strict inequality. So this concludes the proof of the theorem. I'm gonna give 10 seconds for things to sink in. Cool. But now, to make things a little bit more confusing, let's remember that I was doing this because I wanted to finish the proof that the norm defined in that way, depending on the inner product, was actually a norm. So I needed to still prove this part. But now it's going to be really easy taking into account what we just proved. So we take two vectors in E. The norm of x plus y can be written in terms of the inner product. We can separate it again and use the same trick, and we get this equality. And now I'm gonna use the brute force basically, and I'm just gonna use the fact that the real part of a complex number is gonna be less than or equal to the modulus of the complex number. So I just made that change. The rest remains the same. And now we have actually bound for this one, thanks to the Cauchy-Schwarz inequality. So I just use the Cauchy-Schwarz inequality. Remember that the Cauchy-Schwarz inequality was telling us that the modulus of this inner product was less than the product of the norms. But basically, this is just writing the norm of x plus the norm of y square. So we have come to the fact that the norm of x plus y square is less than or equal the square of the sum of the norms, which is equivalent to what we wanted to prove. So we have seen that whenever we have an inner product space, we can define a norm. And there is one more thing that is going to happen whenever we have an inner product space. This is called the parallelogram law. It's another inequality that is really useful. And it's called the parallelogram law because it mimics a law in geometry that is called the parallelogram law or the parallelogram equality. And basically, this law tells us that whenever we have a parallelogram, if we add the square of the two diagonals, that is going to be the same as adding the square of the four sides. Now, because we have a parallelogram, the four sides are going to be the same 2 by 2. So this is where this is coming. And this x plus y is going to give us one of the diagonals, and x minus y is going to give us the other one. So basically, we are saying the same. The only thing that is that in geometry, that law was stated for 2 dimensions. But we're actually seeing that it doesn't matter the dimensions, because at any point I'm making any assumptions about them. The only thing that I'm assuming is that we have an inner product space. We have a sort of parallelogram law. I'm not going to prove it because with what we have saw, the Cauchy-Schwarz inequality and the properties of the norm, this should follow easily. It's a nice exercise. In the references that I'm going to give in the end, you can see hints on how to prove it. And I am more than happy to write something down for somebody if it's something that you feel you need or you would like me to do. But I think this is a nice thing to think about. So for now, I'm just going to not give a proof. Cool. Now we're going to talk about convergent sequences. First of all, a little reminder. A sequence is basically a list of objects of a non-empty set. And this list has a defined order. If we change the order, even if we have the same list of objects, then we have a different sequence. Mathematically, this is defined as a map that goes from the natural numbers into this non-empty set. And we have a map F, so we say that Fn is the nth element, whatever that is. We know a lot of sequences. We know probably the most famous one is the Fibonacci sequence. So this is a concept that should be familiar to everybody, to all of us. I am giving the mathematical definition because in some of the literature they might use this definition at some point, but normally just by understanding that is an ordered list of objects, it's more than enough. Cool. What is a convergence sequence now? Basically, intuitively, a convergence sequence is gonna be a sequence that is getting closer and closer and closer to a limit. Now, there are several important things in here. How do we define the closer and closer and closer in this abstract setting where we are talking about norms and not about actual measures? Well, closer and closer and closer means that, first of all, the limit has to be in the space that our sequence lives. Now, for every epsilon, whenever you see an epsilon, we are talking about really small quantities. There is going to be a positive integer such that all of the elements of the sequence after that one, so all of the n greater than now, are going to be epsilon close to that limit. So basically, what we are saying is, whatever small measure we take, all of the elements of our sequence are going to be as close to the limit as that measure, apart from a finite number of them. And now I'm going to give you a confusing definition because it's going to sound basically like the same. Now we say that a sequence in a normal space is Cauchy if for every epsilon, every very small quantity, we can find a positive integer such that all of the elements greater than that integer, we have that the elements of the sequence are very close to each other. So now we don't have an element in E that we are converging to, but we are getting closer and closer and closer and closer to each other. And now logic says that if they are getting closer and closer and closer to each other, they are getting closer and closer to something. So there should be a limit. That's not exactly how it is because we could have a hole, and we're going to see an example right now. If we're in Q with the absolute value as a norm, this is a norm space. And if we consider this sequence, this is a very convolvulated form of writing the truncated decimals of pi. So x1 is going to be 3, x2 3.1, x3 3.14, and so on. Then this sequence is Cauchy. They are getting closer to each other all the time because they are getting closer to pi. But it is not convergent because pi is not a rational number. However, this very same sequence, if we were in R, it would be convergent. So this leads to the following definition. We say that space E is complete when every Cauchy sequence has a limit in the space. And a complete norm space is called a Banach space. So of these two, R is actually complete because any sequence in R that is Cauchy has a limit in R, but Q is not. We just found a sequence that is Cauchy, but it's not convergent. Sorry. Cool. And now, finally, we arrive to Hilbert spaces. So what is a Hilbert space? A Hilbert space is a complete inner product space. So let's do some recap. A Hilbert space H, from now on, whenever you see an H, you know that that's a Hilbert space. is a vector space over a field, normally are or the real numbers or the complex numbers. We know that it has an inner product. It is a norm space with the norm induced by the inner product. So the norm defined in this way. And it is complete. So we can see from here that every Hilbert space is a Banach space, which is something really useful because Banach spaces have been very widely studied, and there are a lot of really nice properties, but not the other way around. So now I'm gonna just state a theorem that I think is really, really nice. When we have a Banach space with a norm, we can actually characterize when this Banach space is a Hilbert space. So this Banach space will be a Hilbert space if and only if, sorry, by that I mean that there is an inner product such that when I define the norm depending on the inner product, as I was saying before, these two are basically the same. So this is going to be true if and only if the norm that we had in the Banach space satisfies the parallelogram law. Remember that I mentioned this parallelogram law before. If this is the case, if we have that the norm satisfies the parallelogram law, then we can define the inner product in this very weird way, where y is just the I is just the complex number I. And this product, this inner product defined in this way, when we define the norm associated to it, is going to be basically the same norm as we had in the Banach space. This is more of a tongue twist to say than to actually understand what I'm saying. Cool. I'm going to move to some example of Hilbert spaces. So I saw that Van Borde talked already about this lazy example, as he called it, which is just the complex numbers and tuples of complex numbers with the standard dot product as the inner product. We also have, so I'm going to go from smaller to bigger in a way. So we have n elements here. We have a list of n elements. We can go to infinite elements. We can consider the space of sequences of complex numbers. So infinite, a vector that is infinite in a way, which are square summable, meaning that we have this inequality. This is just to control what is happening. And we can consider the inner product given in this way, which, if you look at this one, is basically the same that we are going. We have n elements in our vectors here, and I cannot think of the name right now. And our vectors were of length n, so we add it up to n. Our vectors are infinite or of infinite length now, so we add, but it's basically the same what we are doing. We are just trying to get more abstracts, the structures that we already have and we already understand. And the final example that I'm going to give is the space of Lebesgue measurable functions, which basically I think in physics, I'm sorry if I'm wrong, but I think they are all going to be, so this is going to be for granted, but as a mathematician, I have to state it. That go from R to C and which are square integrable. This square integral is just integrate the modulus of f squared. And the inner product is going to be given in this way. It's just the integral of f times g of x complex conjugate. Now, I'm sorry because I'm going to move back again, but if we check this, it's very similar. We didn't have a function. We had a sequence, but what we're doing is the sum up to infinity of elements times the complex conjugate of the second one. And in here, we are doing the equivalent, which is the integral up to infinity or n minus infinity of the first element times the complex conjugate of the second one. So again, like these are really useful. And what we are trying to do with the Hilbert spaces is basically to expand a structure that we already understand. Rn, Cn, we already understand that. And we are trying to move it to an abstract setup. But whenever you are finding yourself confused about this, just try to come back to the basics. Try to understand something that is happening in a space that you already know and are comfortable with, and then you can move forwards. This is where I'm going to finish today. And before I finish, I want to say that this is, for this part, the bibliography that I recommend. Megginson is great for Banach space theory. For things related to Hilbert spaces, I would recommend the book written by Nicholas Young. And this introduction to Banach spaces and algebras, written by Alan and edited by Dales, is really nice because it goes with a lot of detail through some stuff. It's obviously more centered in Banach spaces and Banach algebras, but you can still find proof of things that are going to be useful because, as we saw, a Hilbert space is always a Banach space. And I'm going to finish here. Thank you very much for your attention. I hope things are clear now. I'm gonna leave the...
Okay, thanks, Maria.
Thanks
a lot. I mean, very good presentation, very good introduction about the Hilbert spaces. And if you guys have some questions, you can write in the chat. And I mean, Maria now also can read, but we are here to try to answer. Bombardier is not back yet. Oh yeah, he's back.
Right, it was right timing. I was like, I'll come back 10 minutes before the session, but yeah, it's actually nice. It was
just
a little bit shorter than the hour, just to give people the opportunity to
yeah, because there were so many definitions that it seemed like if I continue, I'm gonna lose everybody.
Yeah, I understand, but this is what we were saying. I was saying in the previous session to say, you will go through the boring stuff because mathematics is built in layer, especially these abstract stuff. So you really need to go through, a tedious, boring concept, but they are necessary for you to be able to understand the advanced stuff. So yeah, so this is it is just the way it is. There's no shortcut. And Maria has done a fantastic job to to summarize it all in a very nice, concise, with the key things that you need going forward. So yeah, I don't know,
especially like I'm a physicist, so when we start studying these things, we start from Hilbert space. So I didn't even know about Banach space or this. So it's very interesting because I'm learning from where these things, from the mathematical point of view, where these things is coming.
Yeah,
I didn't know about that.
Yeah,
we start like this is Hilbert space, and it works like that, and okay, do the calculations now.
Yeah.
And also, there's a sub. Yeah, go ahead. Sorry, Carlos.
No. So that's why it is really good, because we see when the things are coming. I mean, from the mathematical side.
Yeah,
we don't see this.
And also, for those of you who have read Introduction to Hilbert Spaces from physicists, you will notice
it's a different game.
it's Also, even on the basics, like the definition of the inner product for the physicists, it's the inner product is linear in the second. Yeah, there is a reason. It's just in the second argument. But that's how they do it. We will come back to this once we introduce the Dirac notation, and in particular, once Maria goes through the Ries representation theorem, we will see there is a let's say a cure for why it's okay to do that way. Yeah. But a lot of the physics books, this is Maria's way is the right way. This is the proper mathematician's way of doing it. But just in case some of you already being introduced to Hilbert spaces through a more physics oriented, don't worry, we will bridge the gap once Maria goes through the Rees representation here, and then once we are going to introduce the Dirac notation, we will bridge the gap between the two.